Hi, my name is Shen Mei. I'm a PhD student in computer science at Oxford Polytechnic Institute, an engineering school near Boston, Massachusetts. My research area focuses on latency and gaming. I did this work with my advisor, Professor Mark Claypool, and researchers from different universities in 3 other countries. Today, I will present our paper, Datasets Moving Target Selection with Delay. We are honored to have this paper included in the MMSys 2021. Latency has been an infamous factor in gaming. It degrades game responsiveness and consistency across clients. It's both annoying as a quality of experience and harmful to performance. Previous work shows that delay as low as 1 to 2 milliseconds can be perceived by humans, and delay around 50 milliseconds is known to affect performance in mouse-based pointing tasks, where players click on the moving target on the screen with the mouse as fast as they can. Here's a picture on the right says, keep calm and blame the lag. That is to say, when you suck at the game, don't worry, just blame the lag. Although this is a joke, it still reflects the fact that latency degrades player performance a lot. Moving target selection means click or press the moving target on the screen with a pointing device. It's one of the most basic player interactions, which is commonly seen in all types of games. For some classic games like Duck Hunt, players click on the flying duck on the screen. Or in first-person shooter games, players shoot the opponent targets. Or in mobile games like League of Legends, players attack the enemy at a position with skill. There are so many more examples on all kinds of games, revealing the importance of understanding the moving target selection. Moreover, moving target selection can be combined with other actions to simulate gameplay. For example, if we combine selection with navigation, we can simulate a broad range of first-person shooter games. To gather data on moving target selection, we built 2 games that allows for the study with controlled amounts of latency, Duck Hunt and Juke. In the dataset, 3 are obtained from Duck Hunt and 1 is obtained from Juke. In Duck Hunt, as indicated in the picture, the objective is to select the moving target, a bouncing black ball that moves with a speed. The user proceeds through a series of short rounds, each time using the mouse or game controller thumbstick to control the red ball on the screen and move it over on the target and select it with a click. With the game, players use a mouse to control the red ball in the 2 datasets, mouse A and mouse B, and a game controller in thumbstick dataset. The target moves at 3 different speeds as indicated in the table on the top. As the delay varies between 11 values as indicated in the table at the bottom. Each combination of speed and delay is repeated 5 times, completely randomized. To assess quality of experience, a single 5-point Likert scale question rates the quality of experience of the last round. Is presented once for each combination. Objective measures of performance recorded are the elapsed time to select the target and the number of clicks required to do so. There are 132 participants on these games in total, and each played 167 trials. The 4th dataset is from a custom game called Juke. It also allows study of target selection with controlled amount of delay like Duck Hunt. Juke has the same objective to select the moving target, a moving red ball. However, Juke's target movement is governed by force-based physics rules, turn angle and turn frequency. The target moves with force-based physics, accelerating in the target's intended direction and with a set limit on maximum speed. The target turn intervals varies between 3 values as indicated in the table. The game adds a fixed amount of delay selected from the 4 different values from 0 to 250 milliseconds. Each combination of Juke intervals, angle, and delay appears 5 times, completely randomized. A single 5-point Likert scale question, how much lag did you experience, is presented once for each combination. Objective measurement of recorded performance include elapsed time before clicking the mouse, and the distance between the mouse and the target when clicked. For this game, we have 53 users in total. Each played 223 trials. Here are the information of the 4 datasets. The first column is the name of the datasets, and then total runs in each of the datasets. Performance measurement, testing conditions include target speed, delays, turns, and angles. The fifth column is the base delay of the input devices captured by the high-speed cameras. The last column is the input device players used to select the targets. Next section is demographic information of our users. This table provides a summary of the main user variables in each dataset, with the columns as follows. Datasets denotes the source. Age is the mean participant age in years, with the standard deviation in parentheses. Gender gives the breakdown of number of males and females, with question mark indicating other or prefer not to say. And skill provides the self-rated skill, which is assessed by a 5-point Likert scale question. Rate yourself as a computer gamer. In total, we'll have 185 users, and 74% are males. The mean self-rating was all above 3.5, showing a slight skew of high ability. Graph on the left shows box plots depicting the age distribution for each dataset. Each box depicts quartiles and a median, with the red pluses show the mean value. Points depicted by the dots are the outliers. The which curves span from the minimum non-outlier to the maximum non-outlier. Most users were relatively young, around 20, reflecting the typical ages of undergraduate and graduate students from the universities where the participants were recruited. The graph on the right shows a stacked bar chart depicting the total number of participants in each dataset, with the blue and pink region having numbers and corresponding percents for males and females respectively. The gray regions are others. The datasets have great potential in using. I will propose 4 examples. The first example is on devices. The mouse A and thumbstick datasets have identical user study parameters, except for the selection device, mouse or game controller thumbstick. This allows for comparison of the effects of the 2 different pointing devices have on selection times. These 2 graphs depict time versus delay, with data grouped by target speed. The x-axis are the total input delays, and the y-axis are the time to select the moving target. The trend lines are for each pointing device tested. Each point is the mean time for all users for that device, delay and speed combination, shown with a 95% confidence interval. Overall, there is an increase in mean selection time as delay increase. This increase appears exponential over the range of delay tested. Comparing the thumbstick data to the mouse data shows the thumbstick as a selection device takes about twice as long as the mouse for the same delays. Comparison of the 2 graphs shows that 2 times elapsed time holds irrespective of target speed. Also, responses to datasets demographic questions can be used to answer queries related to user background experience and attributes in relation to game-specific data. Since each dataset included a question, rate your ability as a computer gamer. 1 is low and 5 is high. Correlations between answers to this question and in-game performance may indicate if self-rated game skills are reasonable indicators of actual game performance. We grouped participants' normalized target selection time by their self-ratings of ability. This graph shows box plots of normalized elapsed time on the y-axis for users clustered by self-rating on the x-axis. The n equals to label on the x-axis indicate the number of participants in each self-rating group. From the graph, the mean and median normalized elapsed time improve linearly with self-rated skill. However, the spread indicated by the boxes shows that some individuals with lower self-rating perform better than others with higher self-ratings. And one way between subjects ANOVA test shows there was a significant effect of self-rated skill on elapsed time at 0.05 significance level for the 5 conditions. Results from the target selection datasets can also be compared to prior studies. Long and Goodwin measured selection time for two different size targets with delays from 49 to 299 milliseconds. They found significant mean effects for delay on selection time, and that the effects of delay are amplified by fast target speeds. The similarities in test settings from the study and mouse A and mouse B allows for a direct visual comparison of results shown in the graph. The x-axis is the delay in milliseconds, and the y-axis is the elapsed time to select the target. Each point is the average time to select the target as the indicated delay. Overall, the results across the three studies present a consistent picture of higher selection time with a higher target speed. Most of the data shows a superlinear relationship with an increase in delay. The superlinear increase occurs at different delays amount, with faster targets seeing a rise at a lower delay than slower targets. This means that the high-speed targets are extremely sensitive to delay. The datasets can be used to model the distribution of the time to select moving targets, providing for models to be used in simulations. We illustrate this by modeling the distribution times for the time to select a target with the mouse using mouse A and mouse B datasets. Since the distribution of elapsed time appears log normal, we use multivariate multi-regression to model the mean and standard deviation of the logarithm of the elapsed times. This allows generation of normal distributions of the log of selection times, which can then be exponentially expanded to generate a distribution of elapsed times, useful for simulations. This graph shows the model-generated data compared to the actual data. The x-axis is the elapsed time in seconds, and the y-axis is the probability distribution. The blue shape is the elapsed time for the empirical data, and the red shape is generated from the normal distribution using the modeled mean and standard deviation. The model has an excellent fit for the data, with R-square at 0.99 and RMSE low at 0.03. Regarding future work, we can combine selection with other gaming actions as building blocks to explore game scenarios. For example, selection and navigation together can form first-person shooter gameplays. With this work, we are focusing on the data collection of selection action. We will also conduct user studies to collect data on navigation. With data available, we will build models for the distribution of the data. We then incorporate the models of the actions and build simulations on first-person shooter game scenarios to predict and analyze performance in FPS games. As I mentioned earlier, this work takes efforts from many people all over the world. We want to say big thanks to everyone who developed the two fun target selection games and who conducted the user studies. And of course, thanks to the 185 participants for the invaluable data. Here is the Git link to the dataset repository. Feel free to take use of the dataset. And thanks for your attention on our work.